3時間。
And you saw the classical definitions. All the reasons I did what is a tensor, that whole sequence, was in rebuttal to this very notation that Dinverno uses without any apology, which he shouldn't, because that is the standard way that this stuff is taught. So the point is that we'll talk about this in one of our early lectures in this series, how the classical notation is used, and we will use it, because to not use the classical notation is really, it's illogical, because all of the books that you are likely to encounter do use the classical notation. The one big exception is one of the best advanced books, which of course is Meissner's Thorn and Wheeler, which I write down as it's Meissner, Thorn, and Wheeler. And of course it's called Gravitation. I say of course because I assume that everybody's seen this book, but that's not necessarily true. The book is titled Gravitation. It's a legendary book. Again, it was one of these things done sometime, let's see, when was it actually published? Sometime in I suspect it was in, I'm not opening it up now, the copyright was in 1970, and the one I'm looking at was 1973, right? And that just shows you how static this is. The key mathematics have been pretty settled on this subject for a long, long time. This is a great advanced book. It's funny because it tries to order the gap between advanced and elementary, and so it has a sequence 1 and a sequence 2, but this is the advanced sequence and this is the elementary sequence. And I don't recommend that you take the sequence 1 version. I think the sequence 2 version is good, so I will call this Meissner, Thorn and Wheeler. This is the way he notes it in here is he puts a little triangle at the top of the page, and if there's a 1 in it, it's the elementary stuff. If there's a 2 in it, then it's the advanced stuff. I think that the 2 section is really remarkable. And in fact, the vast majority of the book is the 2 section. The 1 section I think is fine too, especially the general stuff about how the relative was invented, but the 2 section is really where you want to go if you're doing that book. Now, as far as other advanced books, there is Wald and Chandrasekhar. I'm not even going to try to spell Chandrasekhar, so C-H, S-K-R. How about that? Take out all the vowels. So Wald and Chandrasekhar, they both have two different books I'm talking about. Wald's book is called General Relativity. That's Wald's book. And Chandrasekhar's book is called The Mathematical Theory of Black Holes. That's Chandrasekhar, C-H-N-D. Now, what's interesting is Wald's book, of course, talks about general relativity. Things simple and advanced, but it does it all much more tricky mathematics. It's very sophisticated. It uses the classical notation, but it assumes that you really have a very solid foundation of things, and most of you by now do. The mathematical theory of black holes kind of takes the most interesting thing in elementary general relativity, or even in general relativity in general. It takes the most interesting thing and talks about the subject of general relativity as though it's all about black holes, which kind of makes sense. So Chandrasekhar was an astrophysicist interested in neutron stars, white dwarf stars, black holes, and so he developed general relativity with an eye towards understanding black holes. So the book is very black hole heavy, but the general relativity part is very similar to Wald otherwise. Anyway, those are some books that I would recommend. I have also produced a book myself. It's about the solution of the Einstein equation for Schwarzschild geometry, elementary exploration of the GMT6 of space-time, and I'll make that available too. It'll help a lot with these lecture notes, because these lectures will be quite parallel to the small book that I've written. So I'll make that available at some point during this when time seems right. I'll make that available free. I don't charge for it. These books you can find in various places. This one I think you're just going to have to buy, right? As far as I know. When you hunt around on the web, you can sometimes find PDF copies of things. Just be careful you don't want to screw around with anybody's copyright. But these are the books. So the answer to the question of recommended books is the answer. Now let's discuss the units that we're going to use in this class. Alright, so now we'll talk about the units used in this system. And some mix of natural units, when we need to use natural, and geometrized units. The important one is to understand this one. Right? This is important for special relativity and field theory, and this is important for general relativity. So we're going to talk about geometrized units. And it's pretty simple. Right? We will learn ultimately that Einstein's field equation can be written the following way. So the Einstein equation will be R mu nu minus 1/2 R G mu nu, where that is the metric, plus the cosmological constant times G mu nu equals 8 pi G over e to the 4 times T mu nu. So this is the formula Einstein equation that we'll learn when we get there. Right now, presenting just to talk a little bit about the units. What the units are going to do is it's going to clean up this stuff here in the back. And what we're ultimately going to say is that the gravitational constant G, which is the familiar one from elementary physics, and the speed of light C, which is the familiar one from special relativity, setting those to be dimensionless and to be equal to 1. So G equals 1 and C equals 1. Now normally G meters cubed per kilogram per second squared. Let me see if I got that right. Force, which is units of mass times unit of distance divided by units of time squared, has to equal G times mass squared divided by distance squared. And the force equals, this is the distance L. So in order for this to work, G has to have units of L. Let's see, L cubed and over mass over time squared, but then there's a mass up top working because I didn't care, right? God damn it. Sorry. This is obvious, right? So this you end up with length cubed in the numerator, right? Like cubed in the numerator, you end up with one factor of mass in the denominator and second in the denominator. Okay, so square. So this is what the units are for the gravitational constant. But we're getting rid of all that, and we're calling it equal to 1. Now, C, the normal units are, I keep confusing myself, is because M, capital M is supposed to be units of mass, but M, of course, reminds me of meters, so I think length, and that's what's coming up. Divided by time units, right? So in order for C to equal 1, units of length time. And notice that then means that G would now be cubed over mass over length squared. So once I do this, then I end up with G is length over mass. Right? So by setting C equal to 1, I'm saying length and time to be the same. The implications for G are that G is now measured in length over mass. But now I'm going to set G equal to 1. So I'm also setting length, units of length equals units of mass, which now obviously by transitivity equals units of time. So all of these things are measured in the same unit, right? Length, mass, and time are all measured in units of, we'll pick length, right? And we'll probably use meters, right? So when I measure the mass of a star, I'm going to measure the mass of a star in meters. When I measure how much time has elapsed, I'm going to measure how much time has elapsed in meters. But I'm going to measure how far things are apart in space-time, I'm going to measure it in meters. Now, the space-time interval is the thing that's a critical, that's the critical number, and you remember that for special relativity. That is something we will go over. But this is the units we're going to work with. We're going to work in the units where G equals C equals 1. And this was motivated by the fact that we believe that now we study nature and we know that C equals 1, right? We know that. And we know that C's constant for all observers. That's what we know. And so we decide, that is so fundamental, we're going to rejigger all of our units based on that principle. It's kind of like changing the denomination of money in a country or something. It's hard to do, because not because it's fundamentally difficult to do, but because we're so used to doing it some other way. And suddenly easier. Now, that's much more arguable because you're really doing a subjective question about whether or not an equation looks easier. In this case, we're actually dealing with something that you can't really argue with. C is such a fundamental part of what space-time is all about, the speed of light in space, or the speed of any self-propagating energy in space. I don't want to say light isn't the only form, right? There could be other forms. For example, if neutrinos didn't have mass, they would all travel at the speed of light. It turns out it's likely that they do have mass, so that's not fun. But for a while, when I started studying this, it was unclear. So this is so fundamental that it's screaming at us to make this the fundamental constant, to measure all of these things in the same units, and that's what we're going to do. Now, there's another unit issue that's probably worth talking about a little bit regarding energy. So let's look at that. Wait, before we look at that, how does all of this affect everything here? Well, we end up losing G and C to the fourth, and you keep this 8 pi. So what's that 8 pi all about? Right? And that has to do with the Newtonian limit, right? Coming back into the Newtonian limit. And the pi's and the 8s and the 4s and the 2s, they show up in the Newtonian limit because of the way the force law was written. Remember, ultimately we had this force law, and the force law was written in such a way there was something called the gravitational potential in physics and Poisson's equation, and there's integrals over spherical volumes, and that's where the pi's start to show up. So it becomes where do you want your pi's to show up? Do you want them to show up in the field equations? Do you want them to show up in Lagrangians? Somewhere. And the place where you put them is actually a distinction. This actually matters more in electromagnetic theory, where you have different types of unit systems. These pi's are being in different places. Not something we need to talk about here, but that's the origin of the 8 pi. Ultimately, is the Newtonian limit of all this. That Newtonian limit has this problem of how to track various integrals around spherical surfaces, and you just decide where to put it. So that's where that comes from. So the rest of this, though, is just that this stuff here, now, what's left, is what we're going to ultimately learn about. We're going to learn about Einstein's field equation, what it means and why it's important. The only thing in this that you should recognize already is this guy, G nu nu. And G nu nu comes from our what is a tensor prerequisites, and it is a tensor field. It is a 1-1 tensor. It is a 0-2 tensor field, and therefore it is understood to be a function of space-time, where x is a coordinate inside of space-time. And then the part about the manifold is that's so important, is that coordinate in space is a property of a manifold. If you have a manifold, which is what we're going to use to model space-time, you can, that's because that's the definition of how a manifold is built. So this is a tensor, a 0-2 tensor field on a manifold. The manifold is modeling space-time. The 0-2 tensor field is the metric tensor, which establishes an inner product at every point in space-time for comparing vectors located in those tangent spaces. If what I just said doesn't make a lot of sense to you, then the prerequisites, you're a little bit behind on the prerequisites for where we're going to go. I'll be repeating these things again as we go, so it won't be like I'll just refer to them without any review at all. But those things I just said should be relatively familiar. Ultimately, this thing here, the cosmological constant, it's probably not something we're going to talk about in the early part of the course, because we're going to go right into the mathematical modeling of space-time and black holes, and not cosmology, not cosmological models. So probably not going to deal with that. We're going to set it equal to 0, basically. But this guy, he's a big part of the story. This 3D tensor is a huge part of the story, same with the curvature tensor. And then there's another tensor from which all of these guys are made, the Riemann curvature tensor. This this guy here is ultimately this is the matter side of the equation, and this is the space side of the equation. This is the matter side of the equation. Right? And ultimately that represents the distribution of matter, where matter is very broadly understood to be mass, energy, light, fields, anything that we can consider anything that's not a vacuum is essentially matter. Okay, but there's another unit issue I want to come back to, and that is the special relativity style questions. So let's have a look at that. So in this tradition of taking fundamental things and turning them into unitless numbers, we have the problem of the charge of the electron. Charge. I'll write down as E, charge of electron. Now, putting aside the issue that E, the charge of the electron, is always treated as a negative number, and probably should have deposited. This is another one of those things that people always, in retrospect, people would go back and change, but nobody really has the stamina to make it happen. But the charge of the electron is evidently a fundamental number in physics, and it's arguably the real fundamental number is 1/3 of charge. Under the core come in with this kind of charge, but because the issues are separated from one another, it is very safe to say that we is the fundamental charge of the electron. And so E is measured in coulombs usually, so in units of C, I guess. I guess we'll call this the fundamental unit of charge, and it'll be coulombs usually. Is normal physics of electromagnetism. However, it's fundamental, so we have the same argument we have with C. Why don't we just set it equal to 1, right? And if we set it equal to 1, then we have a cascade of unit changes just as we did here, right? And what does that cascade work? Well, we begin by saying that energy has a unit, and that energy unit is going to be one unit of charge accelerates through 1 volt, and we'll call it the electron volts. So that would be our basic unit of energy. So the basic unit of energy is the electron volts. That's telling us that we're measuring the charge of the electron into of unitless number 1. If we didn't, then basic unit of energy would be something like joules, right? Where we know the charge in coulombs and distance in meters and time in seconds, right? So we're not doing that. We're going to we'll keep the meters and seconds maybe, but the charge of the electron goes to 1, so joules ends up being electron volts in that circuit. Now, so what does this now imply? Well, energy is and we've also made the choice that C equals 1, right? But the problem is that we now know that energy is also equal to mass, right, times C squared, right? Energy is mass equals MC squared, right? Energy is mass times C squared, but C squared is 1. So we end up with this idea that mass is also going to be measured in electron volts, right? But now we're talking about special relativity, so G is out of it, right? We're not talking about G now. We've only set C equal to 1 and E equal to 1. So mass has to also be measured in electron volts. And that makes a lot of sense because we always had this equation, this idea, this E equals MC squared idea, which basically says energy can be directly proportional to mass, and the constant proportionality is C squared. But if we make C squared 1, then we get energy equals mass, right? Now, the other problem with this, though, is we end up with momentum, P, right? And P equals mass times velocity. But velocity is now unitless, right? So the units of momentum have the mass, which is units of energy. In the special relativity system, this is the special spectral, right? And so our equations in special relativity, that's where when you use this, equations become much cleaner. You end up without all of these little C squares everywhere, or C powers everywhere that you do see in the most elementary treatments of special relativity. You may want to redo some of that, go to a different book that actually uses this system of units, which are called natural units, and start over and review it using this system of units. We won't have to do this much. Did I say what this was called, geometrized units? I'm not sure I said that. This is geometrized units, and that's the units we're going to use. Okay, so what else do we have to talk about as a preliminary matter? Well, I guess we could talk about sort of the syllabus thing, right? And I will confess that I don't exactly know the way to go through this. There are 2 choices, though. Roughly speaking, the way I see it, there's 2 choices. There's the Einstein equation, right? A pi t mu nu. We can start by discussing general relativity in general, come up with some motivation for the Einstein equation, which is actually pretty hard. Remember, Einstein thought a lot about this thing. Why so much of it came up with it on direct, right? So there's no just automatic method to go from point A to B and derive the Einstein equation straight from some fundamental basic principles. Arguably, you can do it. You can go to the equivalence principles, other things like that. But it's very nonlinear, and it's almost philosophical. And you're really basically kind of saying, hey, I think the universe operates through tensor equations, and this is really the only logical tensor equation that works. And it
国道的ね 撮ったのかね。無事下山できました。
Symbols, I would kind of give some lip service to that. Or another. There's something, all the books do it. All Meisner Thorn Meisner, it's about the equivalence principle. Devanro's got some really great chapters. I know his handling of it. We'll probably go through these and discuss them. But my insight into this is certainly not going to be anything different than these books. And this is a very good hypothesis equation of how the universe works, and it's very fruitful in the end. So we can talk about that, and then we use the Einstein equation. The goal of that whole thing, arguably, but the way I would do it in my course, is to learn how to calculate the structure, I'll put that in quotes, of space-time. And when you talk about the structure of space-time, you only need one thing, the metric. You use the Einstein equation to calculate the metric. I'll put a little X there to show that it's a metric field. And the way this is, the theory here is that the mass distribution, the energy distribution in space, and from that I calculate this Einstein tensor, and from that I extract